Hello from Belfast Loch. This is just coming out of the Irish Sea. I figured if I didn't do this now, it wasn't going to get done for another week or so if I got out of the habit. So here we go. We're going to look at infinite potential square wells, and I have one here. So here we are. This is the square well. So this is a graph of this function here. So we have our spatial dimension. This is a one-dimensional square well we're talking about. Now it looks like it has two dimensions, which is a bit confusing, but x is our one spatial dimension, and this is telling us what our potential is at. So there's really only one dimension. So here we have the potential. Energy is 0 inside the well, inside this space from 0 to A, but it's infinite outside at C. As soon as you get to the end, it goes whoosh, right the well. See in the middle here we have a free particle. So it's not free in the sense it can go anywhere it wants, you know, it's restricted by these infinite potential walls. It can't get through. There's infinite energy here. It can't break out, but because there's zero potential here, there's zero energy, nothing's affecting it. It's moving completely on its own, allowed to do its own thing within these confines. So first thing we'll look back at is the time-independent Schrodinger equation. So this is a one-dimensional case here that the particle is just going back and forth inside this box. So here is, I did a video on this a couple of days ago. It's the time-independent Schrodinger equation. We have energy with respect to the spatial dimension multiplied by the wave function with respect to the spatial dimension is all of this. So how can we interpret this in this case with our free particle? Well, we know that potential is 0 inside the well, which is where our particle is. So we can say that this is 0 for all those values. And we know that potential is infinite outside of our walls. So if potential is infinite here, and this wave function term had a non-zero value, then this energy would be infinite, which wouldn't make any sense. So whenever potential is infinite at the edges of the walls, this wave function is 0. So this becomes our Schrodinger equation for this case. I've done a wee bit of swapping about with this term here, but that's just it. I put this whole term to 0, and that's what we've come out with. So yeah, the solution for a particle, the wave function solution for the time-independent Schrodinger equation is given by this expression here. Wave function is equal to A, which is just a constant. It can be a complex or real or whatever. A times sine k, which is the wave number, times x plus b, which is another constant. Can be real or imaginary. Complex multiplied by cos kx. So we already talked a little bit about the boundary conditions in our case. So at x equals 0 and a, the value of the wave function is equal to 0 from what we talked about here. So it has to be 0 or else the energy becomes infinite, which doesn't make any sense. So we know, yeah, this is what it's just saying here. So we plug what we know there into this solution, and we get a sine kx plus b cos kx is equal to 0. And that's for these values. Anytime x is at 0 or less than 0, or anytime x is at a or beyond a. But the beyond doesn't really matter because we can't go there. We're more interested in the equals parts. So when x is 0 or a, this is what we can say, this expression here. So if we do that, if we put x is equal to 0, look at that case first, we see that b goes to 0 because if x is equal to 0, this part goes away because sine of 0 is 0, and b must be 0 because this is a value of 1, or of 1. Or no, not necessarily, it's got a real value. No, it's of 1, yeah. So yeah, we see that B is 0, but what about A? So we see if x is equal to a, small a, as in the length of the box, then the wave function is equal to big A sine ka, which is equal to 0. And that can have two solutions. One solution is that a is equal to 0, and the other is that sine of ka is equal to 0. Now I've crossed this one out because this one is non-physical, because if a was equal to 0 and b was equal to 0, then the wave function would always be 0 and our particle wouldn't exist. So let's work on the assumption that our particle does exist because it does. And that's what I've written here. Let's read this backwards. Yeah. So what that means is this is our solution. Sine of ka equals to 0. And if you're familiar with the sine function, it should be, give us the solution that k of a equals 0 or pi or 2 pi or 3 pi or 4 pi on forever. So now let's look at k for a minute. I derived this in the Schrodinger equation, but k is a wave number. It's the number of waves per meter or per unit length or whatever it is. 2 pi's to cover for swapping between radians and whatnot. So that's k. We also know momentum is equal to Planck's constant divided by wavelength. So we can cancel the wavelength out there and get k is equal to momentum divided by modified Planck's constant.
Good afternoon, ladies and gentlemen. This is the captain speaking. The ship is now entering the Victoria Channel and will commence our approaches down to our berth to Victoria Terminal number 4, and we will be on the berth on time 17:45. I trust you have enjoyed your time aboard today, and especially aboard Stena Superfast 7, and we hope to see you again in the near future. Can I please remind you that access to the stairwells and the vehicle decks is not permitted until a further announcement will be made regarding your disembarkation. Once again, thank you for sailing us today at Stena Line, and please have a safe and pleasant board journey. Good afternoon.
Okay. So there we go. So we can substitute those and get k equals to momentum divided by the modified Planck's constant. We square that, k squared equals momentum squared times modified Planck constant squared. Momentum is mass times velocity. So we get to here. Energy, kinetic energy anyway, equals half mv squared. Kinetic energy is what we're dealing with here because we're assuming there's no other forces acting on it, right? It's a free particle. There's no heat energy on it. There's no blah blah blah. So then k is equal to the square root of 2me h bar squared. We also know that k equals n pi divided by a from our discovery here. K equals integer times that. So, and this is for n equals 1, 2, or 3, so a particle always exists. It's never 0. So yeah, and we make them equivalent and do some swapping around of some bits and bobs. We get E is equal to n squared times h bar squared times pi squared all over 2ma squared, and we can swap that pi squared factor around from our h bar and get this nicer expression here, and that's for n equals 1, 2, 3, 4, 5, 6, 7 positive non-zero integers. There we are. So what can we determine from that? Well, we can determine that the particle in the infinite potential square well is only allowed discrete energy values. So unlike the particle in a normal box going back and forth at a macroscopic level, from what we understand, it can go any speed, it can have any amount of energy. When you bring that down really, really small, you start to have discrete energies that you can have. And also notice we can have no combination here that makes this 0. So the particle always has energy. and it's in discrete values. So just for completion, let's go back and find A from our solution. We found B and found it to be equal to 0. But what about A? So we get our wave function here and plug in what we know about K. So we then, to make this physical, to make this an actual probability amplitude here, we need to make it equal to 1. We need to normalize it. So here we are, we integrate it over infinite range. So it's normalizing it. And we get that, that A, this constant we're trying to find in the solution, squared, multiplied by A, small a, the length of the box, divided by 2 is equal to 1, which gives us that A is equal to root 2 over A. So our solution, hold on, too many bits of paper. Yeah, we have this solution is equal to, forget about the cos, it's equal to square root of 2 over A multiplied by sine kx. So if we look back at our normal expression of any kind of wave, we know that this term is our amplitude. So that's told us what our amplitude is. We see that this amplitude will decrease as the box gets longer. So the energy gets spread out. If this box is long, it has less energy to go up and down from that discrete energy. And if we make it smaller, it can't spend as much energy doing that there, so it goes up and down a whole lot more. But that was just for completion. The main thing to take away is that particles, whenever you bring them down to a small enough space, then they can retake discrete energies, which is a big deal.